Hello, everyone. I'm Renee Yager, Director of Marketing at EPC, and welcome to today's webinar, The 48-Volt Revolution, GaN for High-Density Computing and Ultra-Thin Laptops. Before we get started, I would like to go over a few housekeeping items for today's event. You will have the opportunity to submit text questions to Alex by typing your questions into the questions pane of the control panel. You may send in your questions at any time. We will collect these and address them during the Q&A session at the end of today's presentation. We also have a few handouts available for download in the handout pane of your control panel. The ebook, eGaN FETs and ICs for High-Density Servers, the how-to app note, Design an Ultra-Thin, Highly Efficient Multi-Level DC-DC Converter, as well as a copy of today's presentation with speaker notes in English and simplified Chinese are all available for download. Now, I would like to introduce our speaker today. Alex Leto is the CEO and co-founder of Efficient Power Conversion. As a co-inventor of the HEXFET Power MOSFET, Alex holds many patents in power semiconductor technology and has authored numerous publications on related subjects, including co-authoring the first textbook on GaN transistors for efficient power conversion. Alex, thank you so much for joining us today.
Thank you, Renee, and welcome everyone. In this webinar, we will show how GaN-based solutions can increase efficiency, shrink the size, and reduce system costs for high-density computing applications and ultra-thin laptops. First, we'll focus on high-density computing. Advanced computing applications for cloud computing, artificial intelligence, machine learning, and multi-user gaming are putting high demands on power converters to deliver much more power in smaller form factors. Silicon-based power conversion is not just keeping pace. Due to the significant performance improvements that GaN offers, a fundamental shift in the server architecture is possible, and that significantly will increase efficiency, shrink size, and reduce system cost. This new architecture reduces energy losses by greater than 30%. And we'll look at this shift and explore the pros and cons of various topology options to achieve the highest power density solutions for 48-volt power in data centers, including buck, LLC, and switch capacitors. First, let's look at the traditional server architecture shown here, which uses rack-based 48-volt isolated and regulated DC-to-DC converters that convert to 12 volts, then a 12-volt to point-of-load converter to the CPU or GPU. Due to increasing power, many server designs, especially those adopted by new hyperscale servers and the latest generation of GPU-based AI servers, are migrating from 12-volt input to 48-volt input on the server board. And let's see what that would look like. Here we see this new topology where the input of the server board is 48 volts. 48-volt input eases the distribution of high power and improves efficiency. The evolution from legacy 12-volt server racks to 48-volt racks reduces energy losses by over 30%. Additional key system-level benefits for 48-volt in-rack distribution are copper utilization and distribution losses. For a given power level and bus cross-section, 48-volt systems reduce distribution bus losses by 94% compared to 12-volt designs. Alternatively, for a given cross-section, a 48-volt distribution bus can deliver 4 times the power of a 12-volt system with the same bus loss. The most efficient way to convert power from 48 volts to point-of-load is a 2-stage conversion with intermediate voltages of either 12 volts or around 6 volts. Next, let's look at topologies that can be used to support this architectural shift. The most common topologies for a front-end system of 48 volts to 6 volts or 48 volts to 12 volts are buck, switch capacitors, and LLC. In this table, we analyze the pros and cons of each. LLC and buck have the highest power density, while switch cap has the worst. The LLC and buck can beat 1,700 watts per cubic inch power density versus about 500 watts per cubic inch with the switch capacitor. The buck converter enables the smallest size, lowest component count, and lowest cost for solutions under 400 watts. However, for higher power, Thermal handling and inductor size could be a challenge for the buck converter. Switch capacitors are inexpensive solutions and very efficient at 48 volts to 12 volts at less than 600 watts. The cons to this design are that it's much more complicated than the simple buck or LLC topologies. Also, the switch cap has limitations at high current and as such is not a real practical solution for systems greater than 600 watts. The LLC offers the best efficiency for over 600 watt applications for both 48 volt to 12 and 48 volt to 6 volt applications, and it's the best topology for V in V out ratios of 8:1 or 10:1. With the shift to high density, space on the server board becomes extremely precious due to more and more content per board. By lowering the intermediate bus voltage from 12 volts to 6 volts or 5 volts, a change in technology from power MOSFETs on the secondary side of the DC to DC converter to higher density BCD MOS power stages can occur. These BCD MOS power stages can go to much higher frequencies, making the point of load smaller, and then they can be placed much closer to the GPU or CPU. This reduction in distance can reduce the resistance between the point of load and the GPU or CPU by as much as 350 microohms. At 1000 amperes, that's a 350 watt reduction in losses. There are multiple topology solutions for a 48 volt to 6 volt intermediate bus. However, as we'll show, the LLC topology offers the best system efficiency and high power density. Here are two solutions already shipping in volume using 100 volt eGaN FETs. The two modules shown from different vendors convert from 48 to 6 volts and are 300 watts in a super small 27 by 18 millimeter size. Both modules reach a very high power density of 1,700 watts per cubic inch, thanks to eGaN enabling 1 megahertz operation. Even though the 48 volt to 12 volt front end conversion is lower efficiency than 48 volt to around 6 volts, it's still predominant for servers due to legacy loads that are powered from 12 volts. The latest servers and AI solutions are already requiring input power of around 200 kilowatts and even more. This requirement puts the switch cap topology at a severe disadvantage since switch cap solutions are really not good above 600 watts. They require a significantly larger footprint and have a higher cost. In contrast, eGaN FETs and ICs enable a small and efficient LLC converter capable of high power due to very small form factor, less losses, and 1 megahertz operation. Again, at 48 volt to 12 volt, the LLC topology is the best solution for greater than 600 watt applications and achieves 98% efficiency. Now let's summarize the topology choices by conversion and power level. The switch cap is inexpensive and very efficient at 48 volts to 12 volts at under 600 watt applications, but has limitations for higher power, and it's too complicated for 48 volt to 6 volts. The buck is the least expensive and smallest solution for 48 volt to 12 volt up to 300 watts. Both the buck and LLC have higher power density than switch capacitors. However, the LLC allows the best efficiency for over 600 watt applications for both 48 volt to 12 and 48 volt to 6 volt. And it's the best topology for V in V out ratios of 8:1 or 10:1. An eGaN-based LLC for 1 kilowatt, 48 volt to 6 volt or 12 volts is sized less than 1/8 of a brick. Now, why GaN for 48 volts? The 48 volt input stage, regardless of topology, requires 80 to 100 volt rated devices. In comparison to silicon MOSFETs, eGaN transistors improve the key figure of merit, area times radius on, by 5x at 100 volts. That improvement results in smaller size and lower cost, or lower radius on in the same size. Additionally, the figure of merit RDS on times gate charge, or QG, is also 5 times better than silicon, resulting in lower losses. Finally, zero reverse recovery and less switching losses allow an increase in frequency for higher power density solutions. EPC offers a full family of 100-volt eGaN FETs for 48-volt conversion with ultra-small size and RDS-on ranging from 20 milliohms down to 3.1 milliohms. EPC also offers an integrated power stage including drivers, level shifters, bootstrap, and half-bridge FETs. This device simplifies design and reduces size. In all topologies with 48 volts input, the highest efficiency comes with using eGaN devices. Now let's discuss how leveraging the advantages of eGaN FETs, such as small size and low loss, enhance the performance of ultra-thin multi-level DC to DC converters to meet the demanding requirements of high power in small form factors for ultra-thin laptops and high-end gaming systems. As computers, displays, smartphones, and other consumer electronics become thinner and more powerful over the past decade, there's increasing demand for addressing the challenge of thinner solutions while extracting more power out of limited space. To address this challenge, we'll first examine the feasibility of adopting various non-isolated DC to DC step-down topologies for an ultra-thin 48-volt to 20-volt power solution. The bottleneck of thinning a DC to DC step-down converter lies in the magnetic components. Designers usually have to either embed them into the circuit board or increase the switching frequency to shrink their size. The former increases design and assembly complexity, while the latter requires advanced switching techniques to maintain high efficiency. Otherwise, it'll incur lower efficiency as well as bigger thermal problems. One topology option, the multi-phase converter, is composed of multiple interleaved synchronous buck stages. This solution allows the use of thinner inductors by distributing the output power processed by the single large inductor in the synchronous buck converter among multiple small inductors. This, however, may not address the loss and thermal issues on the inductors, as the volt seconds on each inductor remains unchanged. The multi-level converter can achieve the same inductor current ripple as a synchronous buck converter with lower switching frequency and inductance. This offers the benefit of reduced switching losses as well as reduced inductor size. Now, let's look at a specific design. We will evaluate the design of an ultra-thin 48-volt to 12-volt 250-watt converter using the two-phase and the three-level topologies, respectively. The design specifications include electrical specs that you see here and a component height restriction of 3.5 millimeters maximum, and they were dictated by the requirements of a gaming notebook application. First, let's discuss why eGaN FETs were chosen for the designs. So, why eGaN FETs? This table compares a 100-volt eGaN FET with two best-in-class silicon MOSFET counterparts. This comparison slightly disadvantages the eGaN FETs because we're comparing 80-volt MOSFETs against 100-volt eGaN FETs. The eGaN FETs have much lower gate charge, no reverse recovery, lower output charge, and are significantly smaller compared to the silicon devices with similar on resistance. Now, why digital control? Well, the ultra-thin converter design employs digital control due to its flexibility, especially in development of the complex control schemes. The three control loops, output voltage, output current, and flying capacitor voltage loops required to regulate the multi-level converter and various circuit protection functions can be easily accommodated. The high time resolution allows for optimal dead time management. And for GaN, whose dead time can be within 10 nanoseconds, is much, much lower than that of a silicon MOSFET and its controller driver. Digital control also enables the use of GaN-compatible gate drivers that have high drive strength for fast switching and high side gate voltage clamping for gate over voltage protection. The operating principle of a three-level topology used to design the ultra-thin converter is shown here. The switching events are at less than 50% duty cycle. Q1 and Q2 have the same duty cycle and are 180 degrees phase shifted. Q1 and Q4 and Q2 and Q3 are complementary respectively. The switch node voltage and the inductor current are shown in the bottom two waveforms. When Q1 and Q3 conduct, the flying capacitor and output inductor are charged up. Q1 turns off. Q4 turns on. The output inductor freewheels through Q3 and Q4. Q3 turns off. Q2 turns on. The flying capacitor charges up the output inductor. And at last, Q2 turns off. Q3 turns on again. Current commutation always happens between Q1 and Q4 and Q2 and Q3. In this way, the frequency seen at the switch node and the input is twice the switching frequency. To design this 40 to 60 volt input, 5 to 20 volt output voltage, three-level converter, eGaN FETs are used to further reduce the converter size and improve efficiency. A 100 volt, 3.5 milliohm eGaN FET is chosen for Q1, as this device needs to block the full input voltage for a short period during startup. 40 volt, 3.5 milliohm eGaN FETs are used for Q2, Q3, and Q4. The converter is switched at 400 kilohertz with the 2.4 microhenry 3.5 millimeter high inductor seeing a frequency of 800 kilohertz while producing a 12.5 ampere maximum output current. Similar to a standard buck converter, the flying capacitor multi-level converter control scheme needs to implement output voltage regulation and output current protection. In order to avoid overstressing any FETs, the flying capacitor multi-level converter controller also needs to maintain the voltage balancing of the flying capacitor to half the input supply voltage during normal operation and startup. During startup, the flying capacitor is initially charged to half the input voltage using an existing voltage sensing resistor network, plus an additional resistor located between Vn and Vcp, and turning on only Q4. More information on this control methodology can be found in the paper referenced on this slide. A photo of the three-level converter is shown here. All components, including housekeeping power supply and current sensor, on the top side of the board, and the maximum component height is only 3.5 millimeters. The total system efficiency at 48 volt input, 12 volt, and 20 volt output are shown in the graph on the left versus output current. At 20 volt output, efficiencies reach nearly 98%. The thermal image of the converter operating at 48 volts to 19 volts with 12.5 amp output current with 800 LFM is shown in the right graph. The maximum temperature on the board is less than 65 degrees. This converter is highly efficient and can carry more current with some forced air. Now, let's see how the two-phase design compares. The eGaN FET-based two-phase converter shown on the left is designed using a two-phase controller and four 100 volt eGaN FETs with two 10 microhenry 3.5 millimeter inductors. The switching frequency is set at 400 kilohertz, the same as the three-level converter to compare the performance. The overall power efficiencies of the two converters, including the housekeeping power consumption at 48 volts input and 20 volt output, are illustrated in the graph on the right. At the same 400 kilohertz switching frequency, the three-level converter achieves 97.8% peak efficiency and over 1% higher efficiency than the two-phase converter, and that represents a 35% loss reduction at full load. The 48-volt input stage for high-density server applications and ultra-thin, high-performance computing requires 80 to 100-volt rated devices. In comparison to silicon MOSFETs, eGaN FETs provide superior electrical and thermal performance, smaller size, and lower cost. The expansion of the power stage family further simplifies design and increases power density. And we can say without a doubt, GaN is the solution for the 48-volt revolution.
Thank you, Alex. Before we get to questions, I'd just like to remind everyone that our next webinar will take place on June 3rd, and the topic will be 3 ways GaN is driving changes in automotive systems. If you haven't already, please visit epc-co to register. Now we're going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions through the questions pane in your attendee control panel. Okay, Alex, our first question is, given the many advantages, what do you see as the biggest hurdle for GaN to really take off in 48 volts?
Well, I think GaN is taking off in 48 volts right now. Clearly, there are thousands of MOSFETs, part numbers that address 80 to 100 volt applications. And in GaN, we only have maybe a half a dozen. So we have fewer parts to address that. Also, GaN really, I'll say, tests the skill of the engineer a bit more than a MOSFET. When you go to higher frequencies, you have to be more careful with your design, your layout. You have to be cognizant of parasitics, particularly parasitic inductances. There are also, quite a selection now of driver ICs for GaN, so that's no longer a problem at all. So I think that we're seeing the ecosystem has caught up with GaN, and now we're seeing very high volume designs out there in the world, and they're achieving very, very good reliability results as well.
Okay. We have a question about the devices. eGaN FETs do not have an integrated diode, is that correct?
So eGaN FETs, unlike MOSFETs have a reverse diode. It's a PN junction diode, but eGaN FETs will conduct in the reverse direction. What happens is it's just the channel that turns on. So the advantage of that is there's no recovered charge, no QRR, which is the minority carriers of a PN junction having to be swept back into the device. So with eGaN FETs, the reverse recovery is instantaneous. That's a huge advantage. You can go to dead times of 1 nanosecond if you want, because you don't have to wait for this diode to recover.
Do you have a better cooling concept in the future?
So we have just put up, I think, you can get it through our website, a new video on thermal solutions for eGaN FETs. First of all, I would like to say that all our devices are chip scale, which means there's no package around it, and there is nothing more thermally efficient than an absolutely naked device. That is the most efficient thing, and we demonstrate that without any doubt in the video. So I encourage you to watch it. But I'll give you a metric here. You can take a 4 square millimeter device, which is teeny tiny, and you can get that thermal system down below 4 degrees C per watt, which is unachievable by any packaged device. So don't take it from me, go watch the video. If you have any follow-on questions, we've got lots of information on how to design a economical and very high power density thermally efficient system with our devices.
Okay. Does EPC have any plans to release FETs with lower voltage ratings like 40 volts or 25 volts?
Yes, we have plans. We already have 40 volt and even 15 volt parts on our you can see them on the website. We are coming out with a newer generation of 30 volt and 40 volt parts, monolithic cap bridges, as well in the summer months. So stay tuned. But there's already a very good family of 30 and 40 volt parts available today off the shelf.
How do you deal with EMI and EMC issues?
So yeah, we get this question a lot, and as a result, we just posted a new video on designing for low EMI and low EMC using eGaN FETs. So go onto our website and look at the how-to GaN video series, and you'll see. But the bottom line is that because we have chip scale packages, if you have an efficient design, you have much lower parasitic inductance than with any MOSFET design, where just the package inductances are 4 or 5 times higher than the total inductance you'll get with a design with a GaN device. The parasitic inductances cause overshoot and ringing. That is the primary energy source for EMI and EMC. So by reducing EMI, by reducing overshoot and ringing, if you reduce it by 1/2, I believe the EMI goes down by 1/4. It's the square of that. I also get the question, but your fast rise and fall times, isn't that noisier? And the answer is actually no. The fast rise and fall times only push out to a higher frequency the EMI that comes from the Fourier transform of the fast rising slope or the fast falling slope. And by going to higher frequencies, it is much less expensive and easier to filter out. So the answer is no, you get better EMI and EMC performance by using GaN, much better.
Okay. Is it commercially feasible to use GaN devices in cost competitive markets such as solar inverters?
Yes. Our 100 volt and 200 volt parts in the latest generation have been priced in volume about equivalent to MOSFETs. We benchmark them all the time, and we're right in the middle of the pack in terms of prices that are in the market in volume. So, you know, it wasn't always true. It wasn't true 2-3 years ago, but it is true now. So go take a look.
Okay. So I don't know if you can see your chat window, Alex, but what are the isolation requirements for on-server board converters? In previous architectures where 12 to 1 volt converter was on board, there was no isolation. Would there be a need now, since there is more power electronics on board, which may increase leakage current, grounding issue, etc., requiring isolation between 48 volt and 6 volts?
So the answer is no. The isolation requirements are for input voltages above 60 volts. And that's a pretty common safety requirement. So no, there's really no requirement for isolation. You'll notice on automobiles, by the way, also no isolation, and they're going to 48 volts as well. So it's a big advantage because by not having isolation, you can improve the efficiency and really increase the power density a lot.
Do you foresee GaN to be self-protecting in breakdown anytime soon?
So our GaN devices have a 20% over voltage rating on them. So, for example, a 100 volt device can be used at 120 volts for short periods of time. And that's because we do not have an avalanche rating. And the reason for that is the avalanche of a 100 volt device is probably somewhere around 250 volts. And that just really has to do with some of the failure mechanisms of GaN. As time goes on and our technology gets better, you will see higher performance devices, and maybe eventually we'll also have avalanche ratings. In the meantime, by having a chip scale package, keeping a tight design with low parasitic inductances, your overshoot can stay inside that window very easily.
Okay. What is the highest voltage you are planning to produce?
I think we have 350 volts right now in our roadmap for launch this summer. And we don't have any plans for anything higher than that right now.
Can the eGaN FETs carry the current needed for server systems?
Yeah, I mean, we have eGaN FETs that have 590 amp, ID max capability. So yeah, these are tiny little devices with incredible current densities. Yeah, I don't know what else to say, but look on our website and take a look at how high current you can get these things at.
LLC converters are soft switch, so where does the value of GaN come from?
So, GaN devices have much lower output capacitance or COSS compared to MOSFETs with the same on resistance and voltage rating, and that means lower energy for ZVS, zero voltage switching transitions, and this results in lower ripple in the transformer. So that means you have a higher effective duty cycle. Also, you have much lower input capacitance, and therefore you have much lower gate drive power consumption. So, in the end, we did a comparison. It's in our book where the difference between a MOSFET and a GaN in a 1 megahertz resonant converter was about 30% lower power losses. And that was compared against an older generation of FETs. I'm sure it's better than that now. But everywhere we go, when you got a 48 volt input, you're always going to get about 30% better efficiency using GaN. Resonant, non-resonant, hard switch, 1 megahertz, 500 kilohertz, doesn't matter. It always comes out so much better.
Okay. 300 watt 48 volt to 6 volt LLC was shown with both half bridge with 2 primary FETs and full bridge with 4 primary FETs. How can these designs both process the same amount of power?
Well, the difference is in the transformer design. The half bridge version uses half the turns and thus will have about, it'll have much higher current, about twice the current, and will need larger FETs. For example, for 300 watts, you might want to use the EPC 2053. The full bridge will have lower current with more transformer turns, and therefore a little bit more transformer losses, and can use smaller FETs, such as the 2045s.
Okay. Is it possible to use these devices in boost converters?
Absolutely. I think that the same advantages that you see in a buck converter are true in a boost converter, which typically, most of them are hard switched. And you boost to 48 volts, you need something like an 80 to 100 volt device. So yeah, and we have lots of customers doing boost converters with these FETs.
The PCB traces under your parts carry very high currents. Do you see any issue with this?
There are always going to be issues if you don't think about it. They carry high current. You can use vias to both increase the amount of copper that's conducting the current and also improve the thermal conduction away from the device. In general, the copper has not limited people from using our devices. If you look at the advantage of having such a tiny device that can get really close to the next power stage, it really offsets any advantage of having smaller copper traces.
Okay. You showed the 3-level converter efficiency is better than the 2-phase converter. How good is the transient performance of the 3-level versus the 2-phase?
So the transient performance is actually better for the multi-level converter because the 3-level converter, the multi-level converter, actually has a buck converter as its bottom stage, and this buck converter is going into an inductor that is much lower inductance. Was 2 like 2 microhenries versus 10 microhenries for the multi-phase. And therefore the corner frequency is much higher. So lower inductance has a higher corner frequency and therefore much faster response capability. So in essence, as long as your controller can keep up with it, the transient response of the multi-level is related to the frequency of the inductor, which is twice the frequency of the buck converter without the multi-level.
Okay. What about using these devices in a front-end converter in a grid-connected solar PV system?
We have devices being used in those things. So the answer is yeah, good idea. It obviously depends on the solar system and the bus voltages used in it, but it's a good application and one that we are addressing today.
Which digital controller does EPC recommend and why?
So there are a lot of them. The one that we use is the microchip DS-PIC 33CK64MP103T. But these DS-PICs 33 series are used in most of our design. They're really small, 5x5 millimeter packages with 36 pins and are very cost effective. So we've gotten used to programming them and they work very well.
Okay. What controller are you using on the secondary side?
You don't need to add one in the secondary side because we use one controller for both the primary and the secondary because the LLC converter, and I assume you're asking about the LLC converter.
Mhm.
The LLC converter it's well defined, and thus really don't need to operate it using a dedicated synchronous rectifier controller.
Can FPGA be used for digital control?
Yeah, sure, absolutely. Just needs to be, needs to have the right, it has to have high enough frequency. It has to have, the right number of, inputs and outputs that are needed. And that's it.
Okay. What is EPC's recommendation on gate driver for the 3-level converter?
So we use the teeny tiny BGA based gate drivers. A couple of good ones are the Texas Instruments LMG 1205 and the UP 1966. And in the case of the multi-level, we used one driver for the 2 lower FETs and then one driver, high side only. And each is used for the 2 upper FETs. And we have a how-to app note on that, by the way. So if you want any details, you can go to our website and go to the how-to app note for the multi-level converter.
Okay. For the 48-volt input converters, does EPC recommend 80-volt or 100-volt FETs?
I think that we don't have a lot of 80-volt FETs, so we're applying 100-volt FETs to it, and as you can see, they're much better than MOSFETs. But I don't think you need any. You don't need anything more than 80 volts on that.
Do you see any challenges with designing the magnetics, and what kind of materials or suppliers are you using for that?
Yeah, I think that magnetics are always a challenge. I think that we can get back to you with the and by the way, we'll answer all the questions via email if we don't have time today. But I don't have right in front of me the magnetics suppliers. I believe that Worth supplied the magnetics for both the multi-level and the multi-phase converters, the ultra thin ones. For the LLCs, those are custom designs, and we don't make those modules, so the people who make the modules did the designs.
What feature of the switch capacitor converter is responsible for its low power density capability?
I think that the real answer is that there are a lot more components. in a switch capacitor. And you've got, I don't know, about twice the number of transistors and twice the number of overall components in a 300 watt switch cap 48 to 12 than you do in a buck converter. So it's about, when you add all the peripheral stuff, it comes out to be about a third of the power density. As you scale up in power, of course, these switch caps just become too large. They take over the whole board.
Okay. Despite having a lower number of FETs, why does the half bridge have the same power density as that of the full bridge? I think that's where you were showing the two solutions side by side.
Yeah. Well, so yeah, the two LLCs, right? And the difference is in the transformer design. The half bridge version uses half the turns and will have therefore higher current and will need larger FETs. So for example, the EPC 2053, the full bridge will have lower current with more transformer turns, and therefore can use smaller FETs like the EPC 2045. But again, your transformer has more turns, so it might have a greater DCR in that case.
Okay. Even though the CGS capacitance of GaN FETs is much lower than silicon MOSFETs, how different is the CDS?
The drain source capacitance is essentially the same. It's not quite, but it's essentially the same as the output capacitance, COSS. And in an earlier slide, we made a specific comparison there. So I'm going to go back to that slide and let's take a look. So this is comparing against best-in-class MOSFETs. And if you look at the QOSS at 48 volts, you can see that it's about half. And remember, these are higher voltage FETs compared to the lower voltage MOSFET. So it's about half.
In the 48 volt to 20 volt and the 48 volt to 12 volt converter, which component is the major source of loss?
So those are two very different questions. In the 48 to 12 volt converter, we're probably talking about an LLC or a buck converter. In the buck converter, the largest component of loss is the inductor, almost always the case. In the LLC, it can be the synchronous rectifiers on the output side. For the 48 to 20 volt converter, the largest losses again come from the inductor, and I think that's probably the biggest one in general.
Okay. How does the RDS(on) of GaN change with temperature increase?
It's about the same as a MOSFET, silicon MOSFET. Between 25 and 125 C, the on resistance will increase about 1.6x.
So there's a multi. I think the question is, do we see dynamic RDS(on) in hard switching?
In our generation 5, we gave a seminar, I think a couple of weeks ago, to explain how latest generation eGaN FETs are designed to eliminate dynamic RDS(on). And I think is it still on our web? If not, the
Yes.
phase 11 reliability. Yeah, so you can see it there. I think it's kind of cool. We could actually image electron trapping. So I encourage everybody to take a look at it. We were imaging electron trapping, and we can show where electron trapping occurs physically in the device and at what electric fields. And so we just designed our 5th generation devices so the electric field stayed below the trapping threshold at our rated voltage, and then we show evidence of that. So I think that it's a legacy concern. And if you go back 10 years, everybody's talking about current collapse, which was sort of the severe case of dynamic on resistance. Then it evolved into dynamic on resistance, and now it's evolving into history.
Okay. Let's see. Okay, wouldn't using a 100 volt device for a 48 volt input be a little bit oversized?
Yeah, it's a little bit oversized. 80 volts is probably the minimum that you want to use because of overshoots and transients and things like that. I think that's if we made 80 volt FETs, they would be a little bit better, and they would be perfectly suitable for 48 volt inputs.
Okay.
Not so for 60 volt inputs. For 60 volt inputs, you really need 100 volt devices.
LLC converters are soft switched. Where does the value of GaN come from?
So the real value comes from two things. The first one is lower output capacitance, COSS. We looked at that a minute ago. It's about half that of a MOSFET. And what that means is there's lower energy needed for ZVS transitions, and that results in lower ripple in the transformer. Or another way to look at it is a higher effective duty cycle. So you can produce power with a higher duty cycle because the thing just switches. It goes through the ZVS transition twice as fast. Now, the second area is the input capacitance. If you're an LLC running at a megahertz, the input power is actually not inconsequential. And in a MOSFET, it's 5x that of a GaN device. So, that can be a very big factor, the CISS.
Okay. Okay, on the page with the 3-level converter efficiency, you're showing it better than the 2-phase converter. How good is the transient performance of the 3-level versus the 2-phase?
Yeah, so the transient performance of the 3-level converter is actually better. And the reason is the 3-level converter it's really the lowest level is a buck converter. But the buck converter is running into a much lower value inductor because the inductor is seeing 800 kilohertz. So because it's a lower value inductor, that the corner frequency, or basically the transient response, is about twice as good. So you really get the transient response of an 800 kilohertz circuit in the multi-level converter compared to the 2-phase, where you really have the transient response of a 400 kilohertz converter.
Okay. In the LLC, are the synchronous rectifiers on the secondary side hard switching?
No, they're resonant.
Okay. This will be very easy for you to answer. I heard that silicon MOSFET can qualify AEC-Q 101, but not GaN. Is that true?
That is not true. I don't know. We have how many? Is a half a dozen or so AEC-Q 101 qualified products, and we're doing more all the time. Our parts have been on cars for years, and that's chip scale, by the way. The chip scale products are every bit as robust and environmentally immune as any packaged part. If you know anything about the environmental immunity ratings, they come in something called MSL, and ours is MSL1, which is the highest rating that you can get for environmental immunity.
Okay. What is the maximum switching frequency possible with GaN FETs?
Well, we have some customers that are doing resonance switching at a couple of 100 megahertz. We also have some customers that are doing hard switching at 70 to 80 megahertz. And in both of those cases, those extreme cases, the efficiencies of those converters is 90+%. So you can really get a lot out of FETs. You can switch a FET. I think Steve Sandler, for those of you who know him, was trying to see how fast he could actually measure. And I think he measured 140 picosecond switching on our eGaN FETs. So that's pretty fast. You can go pretty high in frequency.
Okay. What digital controller does EPC recommend, and why?
All right, well, let me look that one up.
Mhm.
Let's see, we have the, it's a microchip DS-PIC33 that we use for most of our designs, and we do it because it's pretty low cost and it's low power consumption. So, when we get to 98% efficiency, you've got to have, just very, very few milliwatts going through your microcontroller. It's, in a 5x5 package, so it's also very small. So that's the one we use, but there are others. There are many good microcontrollers.
Okay. What is EPC's recommendation on a gate driver for the 3-level ultra-thin converter?
So for gate drivers, we use the LMG 1205 from Texas Instruments, or the UP 1966 from UPI. That's a Taiwanese-based IC company. And in the case of the multi-level converter, one driver is used for the lower two FETs, and then one driver, high side only, each is used for the two upper FETs. We also have a how-to app note on that one. And Renee, what's the name of it? How to build an ultra-thin multi-level controller, something like
Yes.
that,
Mhm.
available on our website.
Okay. How's the failure rate of GaN? Do you have a fit value or PPM number in automotive?
We have um, we have an extensive number of fit values for different conditions and acceleration factors if you look at our phase 11 reliability report. But the sort of the bottom line number is we've tracked products in our automotive and telecom applications for several years, and over 5 billion devices in those two applications. We've had an absolute total of 3 failures in the field, and that's 123 billion logged hours. So if you want to look at that as a fit rate, that's 0.02 fits, which is about 2 orders of magnitude lower than anything reported in a power MOSFET. And I would encourage you to look at the phase 11 reliability report, because it shows all of the different stressors and all of the different intrinsic failure mechanisms for stresses like voltage or current or humidity or mechanical pressure. And we really do separate it out by the fundamental intrinsic failure mechanisms. And over the last 10 years, we've made each generation more and more robust by focusing on reducing the sensitivity to those failure mechanisms. It's also how we got rid of dynamic RDS(on).
Okay. You've showed a 3-level converter and then the dual phase buck converter. Which of those would perform better in terms of EMI?
I think the EMI would be it would be the same. EMI is generated from a few different things. One of them, and there's a lot of misconception about it. So eGaN devices from EPC have no package. A typical package, even your best MOSFET package, will have about a nanohenry inductance in between the drain and the source. So that's added to your power loop. What that does is it causes overshoot in your power loop, in your switch node. And that overshoot, the energy in that ringing and overshoot, is the primary source of EMI and EMC. With GaN, the entire power loop is usually under 250 picohenries. And remember, the package alone in a MOSFET is 1 nanohenry. So we have much lower overshoot. An easy comparison, it's about 70% overshoot in a MOSFET design versus about 20 to 30% in a GaN design if you do a good layout. So we've eliminated the primary source for EMI. Now, a lot of questions come up about, well, how about the faster switching speed? Doesn't that increase your EMI? And what happens is, the faster the switching speed, first of all, the lower the energy you have in the switching transition. But secondly, the Fourier transform of that switching transition is out at higher frequencies, which typically requires smaller filters and less expensive filters. By the way, I think we just put a video up on
Mhm.
EMI and EMC using eGaN devices. So take a look at that. That's up on our website in the video series.
Yeah, there's a how-to GaN, and there's also there was a GaN Talk blog post that just went up today regarding
Right.
EMI. So you can check
But
both of those
has
out.
been acknowledged by many customers, EMI is better with GaN than with MOSFETs. It is an improvement.
Okay. Is there a plan for making the gate drive circuit of GaN FETs more robust? I think this is regarding the 6-volt max and
Yeah. Well,
uh,
so the answer, first of all, the answer is that it is pretty darn robust in that we have had 0 field failures for gate, 0 in all these years. In 10 years of production, 0. So they're pretty robust. If you take a look at how we came up with our 5-volt or our 6-volt max on our gates, it really comes down to a desire to have 0 failures ever. And if you run our devices at like 5.25 volts, they're fully enhanced, and you will have less than 1 ppm failure in over 10 years. So we're really rating it to make sure that it never fails, as opposed to just rating it because we're taking into account huge amounts of overshoot. Now, in the early days, that was a bit of a problem because people had to roll their own drivers out of discrete components, and it was a little bit harder to get a good layout. And so those were very, I mean, we had to really work hard to stay inside the 6 volts. But nowadays, with all the driver ICs available, they already have over voltage protection for the gates of our devices, so they never go over 6 volts. So A, they are robust, and B, we rate them more stringently than MOSFETs, and C, the ICs that you're going to wind up using for gate drivers will take care of it anyway.
what is the failure mode when EOS occurred?
Well, EOS is a catch-all. It stands for electrical overstress. And I'll refer you back to the phase 11 report. I mean, if you do electrical overstress from drain to source, there's one failure mechanism. If you do an electrical overstress from gate to source, there's a different mechanism. The gate to source tends to fail through a dielectric failure that is between the gate metal and the field plate. And we have pictures of that. We show that. And in drain to source, the failure mechanism, if you go to much higher voltages, tends to be an increase in on resistance. This is dynamic on resistance, but as I said, we've designed it so that doesn't kick in if you stay inside our rated datasheet limits.
Okay. What is the package inductance in the EPC 2045?
0. There's no package. So we have no package inductance, and the internal inductance in the product is like about 2 or 3 picohenries. It's virtually 0. So all of the inductance is the inductance that the designer adds in the PC board and other components.
Okay. All right. Okay, this one just came in. If customers request some software support for the digital control, can EPC recommend some MCU vendor who has good know-how in power digital control that can provide this type of support?
Yes, we can. We certainly can. We partner with Microchip on several designs, and they are definitely available for support, as are we. If you send us an email, what's the email site for getting any information, Renee?
It's info@epc-co.com.
Oh, hard to remember. Anyway, send us a note, and we'll hook you up with a software
Yeah.
person, either inside EPC or inside, might be Microchip, for example.
Okay. So that was the last one in the queue. So I will, we can wrap it up, I think, for now. So thank you, Alex, very much for your time today. And thank you, everyone, for attending the webinar.